Hello, I'm Sitsudet from Riddle Communication. Today, I'm going to share with you my experiment with asynchronous Internode media transfer with Libfabric. Right. We all know that the broadcast community is moving toward a software-based computing, right? We want to do our broadcast process in a COT server. But if we take a step back, this is not different from HPC. They've been doing this for quite some time, moving big chunks of data around. The only difference that we have, right, is the data that we're sending is sustained, right? So what we really want to do is to have a process that is a compute node, right? We have some data here. We want to send it to another process. That data moves there. And we want to do the same thing, right? As seamlessly as possible, internodes. Pretty straightforward, right? And you know that there's the DMF initiative by EDU. We've been contemplating solution like Libfabric for some time. So shout out for the EDU guys. I don't know where they are. Right. So Libfabric, right? What does it give us? It's a framework that does help us with memory sharing between compute nodes. It is a Open Fabric Alliance initiative. It is a API that is application driven. It is low level enough. It abstracts diverse networking technologies for us. It is supported by most operating system, be it Linux, Mac, Windows. It also can be used in the cloud or on-prem. But most of all, it abstracts all this networking stuff, and that's us, application vendors focus on the data, on what our application would look like. So a brief history. It has been developed, like I said, by the Open Fabric Alliance. It has been launched in 2015. It is an active open source project. It has close to 200 contributors, and it has been used within HPC since 2018. So I'll go to a brief technical introduction. Bear with me. I know it's the last day, so I'll make it this quick. I'm just going to do a quick recall about the asynchronous programming model, right? In the network world, right? Asynchronous programming model, or how we transfer data asynchronously, is the most efficient way to do this, right? You have data you want to transfer, you put in a work queue, and then you leave it there. You don't care about this, and then you, as a compute, you do something else, right? You don't have to do a blocking and wait for that to go out. So you can multiplex multiple workloads. So what is the fabric? It is composed of two parts. The application API, which is basically a standard way how to communicate with the providers, which is the second portion. That's the actual implementation of the technology, right? If you want to do shared memory or whatnot, those are the providers that we all communicate in the same way through the API. So then, like I said, right, the providers are implemented by multiple manufacturers. You can have shared memory providers, TCP providers, UDP, verbs, which is RDMA, EFA if you use AWS, or you can even extend that and build your own. If you want to do, let's say, 2110, it's up to you. You can do that, and then we'll have a common API to access your stuff. So how do we select a provider? It's a simple line of code, right? It's you pass the argument, TCP, verbs, EFA. It's one line of code to select a provider. And then how do we know what provider we have? It has an API or a binary that will discover these providers for us. If it's the binary, then it's the get info binary, or in the code you can call the function phi get info. Here on my left, on my left, there's an example of a provider that lives on one of our machine lab. So we can see here it's TCP, UDP, shared memory. And then the transfer API. There's the two-way operation where both target and receiver are, involved. It's a sender and receiver operation. And there's the one-way operation where only the initiator node is involved, right? After a setup. It requires also memory registration, meaning that the receiver will tell the sender, here's the memory, you can access it, I don't need to be involved anymore. And then there's the collective operation. It can involve a numbers of peers. It also support complex operations such as read, modify, write. And the communication API, you can use it in a standard way with like WebSocket, where it is the connected communication, right? Or the connectionless, right? Where you establish a record of destination and then you just write to it. The second peer doesn't need to be involved at all. Completion API, as you remember in the past, a couple of slides, we have a completion queue. So you can either do a blocking call where you would send data, then wait for the transfer to be completed, but that would leave you to the OS scheduler, right? So you might have jitters while you wait for the data, or you could do a non-blocking call, right? You would just pull a flag within the API and say, oh, that's done. But then you have to choose what's the frequency if you want to do, you want to waste CPU cycles or not. So there's multiple ways to see if the transfer has been completed. So memory registration. So if we use Libfabric with hardware offloading, there's no way if we do that to tell the host not the host but the host memory, right? We have to have a way to tell the US not to touch that portion of the memory, right? Because it is offloaded to be transferred by hardware, a NIC or something else. So this is where memory registration happens, right? We tell the OS, right, this memory will be used by somebody else. Don't touch it. And bonus points, we get also, security. So if you take a step back, where the sender would be able to write to a receiver without the receiver to be involved. If everybody had, the information, you would be able to write to that specific memory, right? So when we register a memory to offload to somebody else, we get a key, and then that specific key can be shared to our trusted peers. So only the one that we allow to write to our memory then gets the permission to do that. So steps to do a transfer. Well, we do the setup phase first. So we create the endpoint, we create the completion queue, we attach that to the endpoint. We create the address vector, we attach that to an endpoint, we add peers, and then we register our local buffer. And then the data transfer happens with one single line of code, send. If you want to receive, it's receive. And then you choose how you want to be notified about the completion. You will either pull or you wait for an event. Simple enough. So it is interesting for us, it is, how it is relevant for video and audio. So we did a simple two use case. On-prem, we had two nodes, using NVIDIA ConnectX 5 NIC through a Arista fabric, and the other one has the same thing. And on the cloud, we use AWS EC2 instance that had EFA enabled through a simple VPC. Mind you, these two setup, we run the same code, right? The same binary. We didn't change anything. We compile it once, and then we put it on these different nodes on these different setup. So for a full HD 60p frame, our target media throughput, if you do the math, would be around 375 or 73 megabytes per second, and the latency would be around 60 milliseconds. So if we look at these different providers, the media throughput is really, really close, right? The EFA being the closest to the media throughput, which is because they use bigger MTU. I think it's around 9K MTU, and then the TCP is around 1.5K. and verbs is around 1K. That's why it explains that, verb has a higher, bit. And on the latency, we're well, below the 16 milliseconds. And we can see also on the CPU usage, right? Verbs and EFA is fully hardware offloaded. So CPU usage is basically nothing. On the audio side, allow me to do like a quick, recap on how we would present, audio memory. It's either interleave, audio samples for the channels. It's really better to do memory transfer. It's more efficient. Or if you're a, audio person and you want to do DSP, those split buffers are really better, right, to handle DSP, functions. But what if I would say, tell you that you really don't have to care about that? Because Libfabric offers what RDMA offers, scatter gather, right? So you would do the unpacking and packing of these audio samples for you. So it's fully offloaded. And bonus point, right? If you want to do use TCP, it does that also, but in software, right? So here we can see that latency for audio, the worst case for TCP is around 80 microseconds, and if you use hardware acceleration, it's well below 30 microseconds. Right? So what's the cost? Right? What do we lose in terms of latency and performance? So we ran tests using pure RDMA and using the Libfabric framework. Here we can see that with different video formats, the cost is about 6 microseconds, right? So Libfabric adds latency of 6 microseconds for a full, video frame. For audio, we're in the same range, right? We test, multiple samples, multiple channels, and we're around, again, 5 microseconds. That's the cost of using Libfabric compared to, pure, RDMA. And what about TCP, right? Again, we're in the same range, right? 5-6 microseconds of added latency. And the TCP world, we're around 25 microseconds for audio, which is pretty good for the flexibility, for the, not caring too much about how we transfer data. So in conclusion, right? What does Libfabric offer us? That's user focused on the data, provides higher level semantics. So you do whatever you want to do as a programmer, right? You do, blocking, non-blocking, you have, standards, socket approach if you want it, and there's no real trade-off. So that's it for me. Thank you.